we will talk about a simple approach to indoor navigation, which is what we are proposing here as the Georgia Tech team. We will talk about the actual algorithms and methods that we have used for control and navigation in indoor navigation, and we will talk about a rapid method for prototyping control software using MATLAB. And we'll finally end with a couple of proof of concept plots and simulation results. So why do we need autonomous indoor flight? As we've already heard, flying robots are highly maneuverable. They're better than ground robots for situations like a fire inside a building or a nuclear plant meltdown, because they're able to overcome obstacles much easily. Like, for example, if there was something here and you wanted a ground robot to approach that, the ground robot would actually have to take the path across the stairs, would actually have to maneuver the stairs, climb the stairs, and actually come here and then find the path directly to the point of interest, whereas a flying robot can fly in 3D and directly go to that point. Flying robots also have the ability to rapidly ingress and egress out of areas, which means you actually have the ability to enter through windows, which ground robots do not have. And if you look at what's happening in today's environments, the needs of the time are that we need to operate more in urban environments, especially with the war on terror and with increasing risks in urban operations. And for these reasons, we need to actually invest and explore technologies in ground robots. So that is the motivation for our interest in this competition. So we started with deciding what are the actual requirements on indoor navigation. So as most of you people know, the Georgia Tech UAV lab has been in the area of autonomous system design for outdoor control and for outdoor UAVs for a long time now. So this is a paradigm change for us. We've been flying outside, and for about, what I would say, 6 to 8 years, we've had many different vehicles now, and we've tried and tested many different algorithms on those vehicles. But flying indoors gives us completely new challenges. The first challenge comes from the size. We have to now restrict the size of the vehicle, which means we are restricted in the amount of payload that we can carry. We need to be extremely maneuverable. We can't rely on things like fixed-wing planes for indoor navigation, because we need to be able to hover, we need to be able to take off and land, and we need to be able to stop and stare at objects. The vehicle that we use has to be reliable. And the control and guidance solutions that we use also have to be reliable, because we don't want that to be an extra source of uncertainty in what we are trying to achieve. And finally, the cost of the vehicle and the control and guidance solution, both in terms of computational cost, the cost of the product in terms of money, and the time it takes to actually assemble and deploy the product, should be low, because the product needs to be an expendable product. Because once you send it inside a nuclear meltdown situation, you're not sure you're going to get it back. So the biggest challenges that we face in indoor flight is due to the lack of GPS. As I mentioned before, we've been dealing with outdoor flight for a long time now, and our systems have evolved to depend a lot on the GPS signal. Flying indoor means we won't have GPS. That means we cannot use a dead reckoning based solution for INS, for inertial navigation. Which means it's really hard to use accelerometers and gyroscopes and come up with basically just integrate those to come up with position and attitude of your vehicle without having an absolute position fix. We need to fly in a cluttered environment, which means we need to take care of obstacles, detect them, avoid them, and reinitialize your paths or replan around the obstacles. We need to have an efficient method of transferring information from the vehicle to the ground station operator, so that the ground station operator is able to take critical decisions without loss of time. And we need a rapid method for testing and evaluating and also prototyping GNC, guidance navigation control software. So if you don't have GPS signal, as I just mentioned before, you don't have a global position fix. You don't have a correction for inertial data from the GPS signal. Basically, the way outdoor navigation solutions normally work is that they use the accelerometers and gyroscopes to get the acceleration and the angular rate of the vehicle. These are then integrated to get velocity, position, and attitude of the vehicle. But most low-cost inertial navigation systems are strapped down. That means they're strapped onto the helicopter. So that leads to a bunch of sources of errors. The first source of error is issues with biases. You don't exactly know what the bias of the sensor is before you begin. The second is you don't exactly know what the attitude of the sensor is before you begin. So normally Kalman filters, extended Kalman filters are used along with GPS position fix, in which you basically compare the position that the GPS gives you with the position and position that your accelerometer integrated to velocity and velocity integrated to position gives you. And using that error, you actually get the navigation solution to give reasonable output. Since you don't have GPS, we cannot rely on that type of method. There has been a lot of research in SLAM methods, which basically means simultaneous localization and mapping methods, which use elaborate sensors, try to map the environment around them, and create a map as well, create a map while localizing the vehicle itself. But they can be highly cost intensive. So we are looking for a reliable and a simple method for navigating indoors. And what we realized that we can use local range sensors to obtain local information. And we can use these local features that are common in many indoor environments to actually navigate indoors. So our idea right now is to use the fact that all indoor environments have walls. If you just start following a wall of an indoor environment and keep following the wall, you will traverse most of the area of the indoor environment. Of course, there has some caveats. First of all, you need to be able to follow the walls. Second of all, the walls should be fairly free of obstacles. But as long as the obstacles are attached to the walls, it's fine. You're basically all you're trying to do is you're taking a reference. As you enter, you take a reference and you keep on following that reference. In this way, you don't really have to have a very elaborate, you don't have to have an elaborate map of the indoor environment. All you have to do is just keep on following the walls and you will traverse most of the indoor environments in a reasonable amount of time. But to do that, you need to have a decent navigation solution. But as I said before, it's really hard to have that navigation solution without GPS. So we decided to tackle this problem from bottom up. So we said, okay, let's look at the vehicles that we can use and see which vehicles are the best vehicles that will actually survive in this type of situation. So the vehicle that we want to use has to be highly maneuverable, has to be sufficiently small, has to be easy to fly, and has to be low cost. And our solution was to use a miniature coaxial rotorcraft. This is the rotorcraft that we use. It's the off-the-shelf Esky Big Llama coaxial rotorcraft. Costs around $120 US, weighs around 410 grams, and has around 18-inch diameter, rotor diameter. The reason we are using a coax rotorcraft instead of a quad rotor or a ducted fan is because coaxial rotorcrafts with the Hiller bar, which is that small thing with the two weights on the top of it, is actually open loop stable. That means if you trim it and if you take your hands off the controller, it'll stay in the trim. It'll drift around, but it'll stay in the trim. That means, I'll elaborate that a little bit better later on, but what that gives us is that it allows us to actually not have to have acceleration and rate information, because the vehicle actually has internal rate damping and that leads to internal velocity damping. This vehicle, the stock vehicle that we saw before, was highly modified into this contraption here, which is called the G-Tar Llama, and Mike Sobers is going to talk about that with our team presentation, what exactly this is. But what this consists of, this is a shot kind of, a picture kind of taken from the bottom of the vehicle. In the center you see the actual hardware and the motors and the avionics of the vehicle, and on the sides the circular rings and the kind of U-shaped flat carbon fiber panels that you see there are actually what we call as the shroud, which is intended, the basic point of the shroud is to prevent rotor damage due to wall strikes. Well,